So for these types of orbital diagrams, we're going to need to determine the electron configuration first for the element, and then we'll figure out how to fill the orbital diagram with those electrons from lowest energy to highest energy. So for beryllium, its electron configuration is pretty short, 1s2, 2s2. All right, so those are our electrons. Now what we need to do is we need to figure out how to fill an orbital diagram. So remember, 1s2, we're going to start with those 2 electrons in the lowest energy orbital. So one arrow or electron spins up, the other electron spins down. 2s2, so that superscript tells us that we need 2 electrons in the 2s, one spinning up, the other spinning in the opposite direction, down. All right, let's move on to one that's a little bit more complex. We're going to go to oxygen. Oxygen's electron configuration is 1s2, 2s2, 2p, and then you have 4. All right, so remember that when you fill in these orbital diagrams, that the superscript here tells you how many electrons are in that orbital. So we're going to have to really pay attention as we fill this one in. It's a little bit more complex. So oxygen, 1s2, so that one's pretty straightforward. We put 2 electrons in the 1s, 2s2, so we put 2 electrons in the 2s. All right, now here's where it gets a little bit different. We have 2p4. So that means we have 4 electrons that we need to put into the p sublevel. It's a little bit awkward when it's written this way simply because you have this x and the y and the z. All right, what's the purpose for that? Remember that the p sublevel has 3 p orbitals. They're all looking the same, they're just on a different axis. I've added this image here where we have the 3 p orbitals. They're just all on a different axis. For example, the x, y, and z axis. They're all the same size, they're all the same shape, the same energy. They're just on a different axis. So if you wanted to, you could actually take this x, y, and z and just black it out. It really doesn't make any difference. We just know that there's 3 p orbitals in the p sublevel. So when we fill out this orbital diagram, we're going to need to put these 4 electrons spaced out as far as possible, because remember, electrons don't like to be close to each other. They want to repel, and they want to space out as much as possible. So we're going to put the first electron, the second electron in a different p sublevel, and the third electron in a different p sublevel. Then we can start to pair them up. So why do we always start with up arrows? Well, according to the Pauli exclusion principle, that is the way we interpret the electrons in the atom. So we're going to go up, 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 down, and that's how we follow Hund's rule to show that electrons fill equal energy orbitals singly before they want to start pairing up. All right, let's move on to a different example where we have nitrogen. We need to find its electron configuration first. We have 1s2, 2s2, 2p, 3. All right, so as we fill in these orbital diagrams, we're going to put 2 electrons in the 1s, 2 electrons in the 2s. Remember, they always spin in opposite directions. Now 2p3. So we know we're going to have 3 electrons in the p sublevel. And don't forget that, yes, the p orbitals are all the same size, shape, and energy, just on different axes. So we're going to fill in those 3 electrons as up, up, up. They're all in different orbitals because they want to space out as much as possible before they start to pair up.